Lab 1, Newton's second law, also known as the momentum principle. In today's lab, we will be looking at the motion of an object in constant velocity. Here is an outline of what we'll be discussing. Please pause to read. Newton's second law can easily be broken down as F net is equal to mass times acceleration. In both of these cases and equations that we have right here, we are able to break down F net equals mass times acceleration to find different things such as our final velocity and our change in position. Here on the left, we have that F net is equal to mass times delta V over delta T, which is our change in velocity over a change in time. Rearranging this, we find that our final velocity is equal to our initial velocity plus F net times delta T over M. And on the right, we have that our average velocity is equal to the change in x over the change in time, which we rearrange to find that our final position in x is equal to our initial position plus our average velocity times the change in time. How we apply the momentum principle. The outcome of this experiment asks us to observe an object at the same speed without changing direction. Because the object has constant speed, the F net is 0. This is because there is not a change of velocity, so in the equation F net is equal to m delta v over delta t, ma becomes 0. We will be using this to predict motion, namely position over time, along with looking at the velocity over time and predicting the position using GlowScript. For our experiment, we just have a ball rolling to the right. Our origin is set here in a later frame to ensure that we have constant velocity, where the right is the positive x-axis, whereas the direction of motion is at. Our initial conditions. We start at a later frame, frame 5, to ensure that we have constant velocity. The ending frame is on frame 25. The frame rate is 30 frames per second, which means that each frame is 1/30 of a second, and the full clip is around 0.667 seconds. The mass of the ball is 0.17 kilograms. Let's take 2 time frames to find our initial velocity. Recall that our average velocity in this first calculation should remain constant throughout the motion of the full length of distance. Down here we have our change in position over the change in time. And notice that we don't start at the origin 0, 0, 0, as we start essentially from our second and third positions over our second and third change in time. But this should still give us our average velocity, as the velocity remains constant throughout the full length of motion. To find our next position, by using the position update formula, we can find that our final position at the end time, in our case, is 0.446 meters in the x direction. Note that our actual final position is 0.443 meters, which is relatively accurate as our change in time is small enough to not cause significant change. Down here, we have our calculation. In the GlowScript code, in this first set of code, we just have our graphs being set up and initialized. No real physics going on right here. Now we begin to set our initial conditions, where our ball's initial mass is set as 0.17 kilograms in SI units. Our ball's position is equal to the vector of positive 0.02 in the positive x direction, and our ball's initial velocity is set at the vector 0.6487 in the positive x direction in meters per second. We also have that our starting time is 0.033 and our change in time is 0.01 for each time we iterate through. In our second part of the GlowScript code, we have our loop which iterates through Newton's second law. We have that our F net is equal to 0 as there is constant velocity. Down here, we also have the ball's final velocity is equal to the ball's initial velocity plus F net over m, the ball's mass, times the change in time. We also have that our ball's position is equal to the ball's initial position plus the ball's velocity times the change in time. At the ending right here, we have t is equal to t plus delta t, which helps us go to the terminating condition as we add 0.01 seconds every time. And the rest of the code is just for the graphs, no real physics. Here we have our first graph, which shows the motion of the ball as it goes to the positive x direction. And here we have our position versus time, where our time is in the x-axis and position is on the y-axis. Note that our graph has a fairly linear slope. Here we have our velocity over time, where it remains constant. As we see at the timestamp 0.1, it has the same velocity as the timestamp 0.6. In this graph, we have Tracker's model versus GlowScript, where we see that the experiment position, the one that we completed and found our data through Tracker, is noted in the blue, and the red is the model position that we found from GlowScript. Notice that as we begin to deviate from the origin and as delta t grows bigger, the calculations begin to deviate and become less accurate, and that in our initial calculations, it is very accurate. Final verdict. We can use the momentum principle to iterate through to predict the future position of an object, but not limited to constant velocity. With the accuracy of the previous charts, we see that as our change in time increases, the data becomes less accurate, so we should use this to predict small amounts of change in time. Thank you.